We know now how to select the adhesive. We should determine the mechanical properties next. We will start with the failure strength tests in module 14.
So we know the main adhesive families, we know how to select the adhesive. Now it's time to characterize mechanically the adhesive. That's very important for the joint design that we will see later in other modules. So let's start with the failure strength tests. And let's start with the most common one, which is the tensile test, which is applied in dog bone specimens like any other material. I have here some specimens, several specimens, you see, dog bone specimens, very nice surface finish, perfect specimen, you can't see any porosity. That's very important to have no porosity, because this will influence a lot the results. So nothing really special about the specimens other than the fact that they are completely free from defects. During the test, you can either use contact devices to measure the displacement or non-contact devices, which I recommend, like a video or laser, because the mechanical extensometers, they might influence the behavior of the adhesive. To obtain these perfect specimens, what we use is a French technique, a French standard, to produce perfect plates of adhesive. And it's based on high pressure, hydrostatic pressure. You have a representation here of the mold that we use, but really the trick, the secret, is this silicone frame, okay, that will avoid the adhesive to flow out, keep the adhesive in the middle, and allow a high pressure on the adhesive. And it works for any type of adhesive, film, liquid, paste, any type of adhesive. You have here the various steps involved in the production. So you pour the adhesive in the mold, you apply pressure, you cure, then after the cure you move the plate, you have the plate here, and then you machine the dog bone specimens. It works every time. About the properties that you get from a strength test, you have here the main ones. So you have stress versus strain. This is the curve. So from the curve you get the stiffness, the Young's modulus, you get the strength, and you get the ductility. This is also used later for joint design. But adhesives are polymers, and they don't behave the same in tension or in compression. With metals you can deduce the compression from the tension. In the polymers you can't. You could do a compression test, but they are extremely difficult to perform. So in general what is done is tension and shear, and with these two tests then you have the adhesive fully characterized. One of the most common shear tests used is the thick adherent shear test. I have here an example of a specimen. So you have the adhesive here, and as you can see the substrates are quite thick, okay? Okay. You have the geometry here. This is a failed specimen. The only difficult thing here is the measurement of the displacement. We are talking about a very thin film of adhesive, and it's very difficult to precisely measure the displacements. Another type of test that is increasingly used is the Arcan test. You have here the device, the specimen is here. I can show you also the specimen here. So you have the two substrates, and the adhesive here is right here in the middle, all right? The beauty of this test is that you can vary the angle of loading. So you can have it like this in shear, but you can have like this in tension, or you can have it at an angle. So you can characterize the adhesive in various modes of loading. You can also test the adhesive in bulk with the same Arcan device. That's possible, but it uses a lot more adhesive, but the displacement is easier to measure. But the shear test that I recommend, because it's free from stress concentrations, is the torsion test. It can be in a butt joint, like this joint here, okay? You have the adhesive here in the middle with the two substrates, and you torsion it like this, okay? This is in the case of a joint, but it can be also in the case of a bulk, and bulk in the tubular form. I have a video for you. Why the video? Because in general, people don't do this type of test. Why? Because a torsion test is quite expensive. But we have developed in the lab a simple one that can test in torsion and is quite innovative. Let's see the video together.
Can you imagine driving your car and having a windshield full by itself? That's what could happen if an adhesive joint is not properly tested. Adhesive joints are known for being a light-fixing material. This means we can replace some of the bolts and rivets we normally use and save weight. This is particularly useful in the car industry, for example, as a way to reduce fuel consumption. Cars, boats or planes are always under heavy pressure when moving, which means it's very important to know how much stress their adhesive joints can endure. It is generally accepted that the stress-strain adhesive properties are better determined under torsion, but current torsion machines are very expensive and were designed to test other types of materials. In the University of Porto, researchers developed a machine for torsion tests specifically in adhesive joints with much more accurate results, and at less than a third of the price. One of the main features is that the center line is in the vertical direction and there's a counterweight to eliminate gravity and weight forces, thus measuring only the torsion angle and torque applied.
The machine can control the force and the displacement applied, so it can do creep tests, relaxation tests, torque rate control tests, and displacement rate control tests.
This technology was developed through a collaboration between teachers and students from the University of Porto. They are now doing torsion tests for many world-renowned companies.
So that's for the video. And finally, you have here a plot in a shear strength strain diagram of the main structural adhesives used. So in one part of the scale you have the strong epoxy adhesives, then you have the toughened epoxies. They are not as stiff as the pure epoxy, but they have an increased toughness. And in the other part of the scale you have the one part polyurethane that can go up to 500% deformation, the windscreen for example. And then in between you have all the other structural adhesives we discussed, the acrylics and the two-part polyurethane. With this graph you have a good idea of the mechanical properties, so from 50 up to less than 10, and displacement or deformation about 5-10% up to 500%. With this you can cover all the applications where adhesives are typically used. So that's for the failure strength tests.